Okay? So right now, I don't get much mileage. I still haven't interpreted this.
When you're writing 5x below the action, are you saying, I know it got pulled out by the derivative, are you saying something about the order of multiplication? I just don't understand
what this is.
Yeah, why is it beneath the exponent?
Because I functionally differentiate with respect to j.
Yeah.
Now, j is got that, so the delta delta j doesn't care about this other variable phi, so it comes through. It just sees an e to the I j phi.
Yeah.
So it says that's the guy I want to differentiate. So differentiate this exponential, and you pull down whatever is in front of the thing you're differentiating.
So you just mean it's to the right of the exponent?
Now, the ordering, the fact that I put it here as opposed to here.
I thought you were putting it as a fraction inside the exponent.
Yeah, that's what
Oh, gosh. Fraction. Yeah, no, it's on the ground. Is that,
it's on the ground.
Is that what you meant, or are you still?
Yeah, I just didn't understand. I knew it wasn't a fraction. I just didn't understand the notation. But I get it now.
So I'm saying exponential multiplied by phi.
Okay.
Is that? Yeah. So it's just there, right? So it's what you would have thought by doing that function derivative. And so I don't care about this and this in general. I care about it at tree level. So So again, by using the stationary phase, approximation on the numerator path integral and on the denominator path integral, I'm just getting, so the denominator is easy, I'm just getting the thing that I got before. The numerator, I'm again doing the stationary phase, saying that if the phi is not stationary, then there'll be wild cancellations from this exponential, so this will be dominated by phi's, which satisfy the classical equation of motion, in which case this phi is that phi sub j. Okay? So then this cancels with this, and this is the guy who I wanted to name. Okay? It says that there's this relationship we have with phi sub j, and let's see. We can choose phi to be the independent variable. So the thing about phi sub j is you can dial it. You can dial it by jiggling the j. Whatever particular phi you want, just keep turning the handle on this j until you get the phi you want. That's what it means to start thinking of. Right now it seems like it's responding to whatever the source is. You give me a source, you'll get a phi sub j out. Phi depends on j. But if I say, no, I want that phi sub j, I want it to be something. And so this something is often called phi classical, or phi CL, or sometimes it's called phi, why I call it phi classical? Because phi sub j is itself something you might think of as the sort of a classical solution in the same way as that word. Or sometimes you see it called phi bar. Why is it called phi bar? Because if you like, in the statistical physics analogy, you can think of phi as the magnetization and J as the magnetic field, the external magnetic field. And you seem to be doing some sort of an expectation of magnetization as it responds to an external magnetic field, okay? And so you think of this phi as the kind of average magnetization in some background, or in some applied external magnetic field. And we're doing a very, similar to StatMech kind of Legendre transform, where we're saying, no, I'm going to tell you what magnetization I want. I demand that you do this. And then the little grad student has to twiddle the J until they get it. Will they succeed? I've demanded some random value of phi bar of x. Are they going to succeed in doing it? Well, they better work out one theory question, right? Which is to say, they need to solve J must then be the solution to delta W tree delta J equals phi, which one shall we go with? Let's say phi bar. I'll go with that notation then. They better find the J as a function of space-time. They better find the J which solves this equation. Okay. If they do that, then they've effectively turned who is independent and who is dependent around. Okay. And we've got the inverse Legendre transform staring at us. Perturbatively, which is all we ever do in this class, this is uniquely, and I think in general it's believed, uniquely solvable because what is the form of this equation? You see, in free field theory, all of us know what W tree is. Okay? W tree is equal to this I integral d4x jx Green's function gx minus y. So, plus order j cubed. I mean higher point functions and this. But guess what? The higher point functions, since they're connected, higher point functions are all perturbatively suppressed. So yes, they're there, but this is the most important term. And so this equation corresponds to g x minus y. Oh, sorry, there's an integral d4y is integral dy d4y j of y is equal to phi bar of x and plus perturbative corrections, which means that we can always solve this equation iteratively in powers of coupling constant, as long as we can solve the zeroth order equation uniquely. Okay? So, question, can we solve this thing uniquely? And you can see that I can just apply this operator, the Klein-Gordon operator, to both sides of this equation, and I find that perturbative I'm not going to repeat what I think I did once, which was to show you how, I'm trying to remember what was that case. Like I was trying to show you that in perturbation theory, the pole in the propagator, in the dress propagator, the pole would not be the same as the mass parameter in the Lagrangian. That would be true at tree level, but not in general. And then I showed in perturbation theory, however, there would be a unique solution to that, finding what the pole was. And if you look at that, that's the sort of, that is a typical classic kind of perturbation theory, like the kind that you learn for perturbations of the hydrogen spectrum and so on and so on. And this is exactly that kind of thinking. But basically, if it's invertible at 0th order, it's invertible. Okay? That's the way any set of equations would work. So, yes, I have there. I've got a solution. Okay. So, these are Legendre and inverse Legendre transforms of each other. It's nice to know that they have a name beyond any sort of graphical thing, because now we can even conjecture, and we do, that non-perturbatively this is the relationship. Okay. So, just some stat-mech equivalences. The gamma W Legendre transform is analogous to the well, here I'll just gamma is analogous to the free energy I haven't yet, sorry. No, this is what I want to do. Haven't introduced it yet. Okay, heck, it's easy to do. Let's do it in 5 minutes, and then you'll see the power of, I think I have everything on the board that I need. So, you will write furiously, and I will just point. Well, look, everything we did, everything we did was at tree level. Non-perturbatively, or even in perturbation theory, I would really like to go beyond this tree level restriction that tells me this interesting relationship between the classical action and tree level. I wish I had something which looked exactly like this, except I could erase the word tree. Then I would be really, cooking. I just need something to replace that action, classical action. Something that took up all the non-classical corrections and made it look like a pseudo-classical action and gave me the entire set of Green's functions, if only it existed, okay? And so let's see what would happen. Let's see how that would work. First, consider the following crazy thing you could write down. It seems like double counting or something, okay? Let's just consider, oh no, I have to define this. No, that's not going to happen in 5 minutes. No, I need to define the effective action for you. What's going to happen in 5 minutes? What can I use this 5 minutes for? Any questions? Okay. But basically, what are we headed towards? We're headed towards the idea of the same kind of thing that you do in statistical mechanics. We have the energy, but we know that energy is not the only consideration because we have temperature. And so, if you like, we are in a heat bath, and you're not always being pushed into the ground state by demanding the lowest energy. But you would like something that fakes it, that makes you think that you don't have any temperature, but you have this modified energy functional. Okay? If I could change the energy and say that all the effects of all those thermal fluctuations, or the heat bath, are subsumed into just saying, pretend there was no heat bath, but there was just a new energy. Life would be great, because I could think like a classical guy instead of this horrible quantum mechanics stuff that I have to do. Similarly here, life looks pretty good as long as we can think about classical actions and classical solutions and all of that. And wouldn't it be great if there was a way to think like that? And all of the h bar could be got rid of. We don't have any more h bar to worry about. And all we do is replace our classical action with some Gibbs free energy-like action, the so-called effective action. And it does all the quantum stuff. All the quantum mechanics is just hiding inside this small change from classical action to effective action. And you get not W tree, pathetic creature that is, you're getting the entire set of all possible correlators by just solving a classical problem, but with a different gamma. Okay? So that's our question that I'll leave you with. Is there a way that I can cross that stipulation off and instead write the word effective here, so-called effective action, and the question is, does it exist so that I just solve classical equations for a modified action and get the answers to a quantum problem? This is the exact analog in stat mech of extremizing a classical energy, functional, but not the one that you started the problem with. Not thinking about temperature and getting the thermal correlators, the statistical mechanics correlators, for free. Too good to be true, but we see it in the form of the Gibbs free energy. And the question is, do we have that in field theory? And we do. And that's the construction that we want to do next. And that is the object that's the closest to where a normalization is not trivial. So that's why we're doing it. Okay, so why don't we stop there.